this this process back into the ground state of the dye molecule. So your sunglasses can go from dark to light and dark to light like this. Okay, so what I'm trying to impress you is that you could have absorption, right? So this is in fact surface chemistry because you excite one material, right? Dye material. So chemistry is important because you can, if you are a synthetic chemist, you can build this molecule. You can design this molecule to incorporate into your material and create all sort of interesting things that change classes. Window technology, smart window technology is one of them, whereby you again incorporate appropriate dye into the window so that it would darken automatically, right? Depending on the light, outside light, how bright the light, sunlight are, it can darken automatically. And that is important to the environment because you can save energy that way by automatic darkening. So-called photochromatic window, smart window. That's another term that sometimes people use. Smart because the idea of smart material is that you have material that respond to external stimuli. So the external stimuli here will be the photon from the sunlight. So and then you create a response. So stimuli and respond is the hallmark of smart material. So photochromatic window is smart material, and that's related not just to soil science but to nanosciences because you can incorporate with nano optic into the window material to create this interface for this basic principle to operate. So I think what people should understand is that you don't need a lot of physics to do this thing, and chemists can do this thing very well, in fact, because you need to understand basic principle of how it works, and that's what the nanosciences is all about, because you can have some basic idea such as this. This is a very powerful idea. It generates a lot of application based on that simple electron transfer idea between one type of material, which is the dye molecule, right, which chemists can build, into material, generic material that you can find. So a lot of the material science work, nanomaterial science work, involve finding out this kind of work, research into this compatibility between these two. And indeed, a significant amount of work going on this campus, and it will involve this type of matching of material, manipulating of material based on simple idea. I mean, this is a rather simple concept that you have. Next, everybody use this in your printer, laser printer, and for Xerox machine is photoconductivity and Xerox gravity. Xerox, of course, have patent on this, a Canadian company, and have this idea that you have a metal back film of amorphous semiconductor. It's all semiconductor related, and you first charge it up. Okay, so you charge up your semiconductor because it's a semiconductor. You can introduce extra charge, right? Because you have valence band and conduction band. It holds the charge on the front end of your backplate. Sometimes it's called fuser in the Xerox machine terminology. It's called a fuser. You just basically where you fuse the ink to the paper. That's the where the terminology comes in. And at room temperature in the dark, this semiconductor had low conductivity. So what happened? What happened is that this charge stayed for a while. And if you have charged up paper, you can see this, right? Because you can, if you have rub your little ruler, if we all done this in primary school, if you rub your ruler by in your clothes, you generate static charge, and the static charge pick up little pieces of paper. So you think of your fuser is semiconductor, is your rub off certain amount of static charge, and the paper is your little toner ink powder that you have. So you then sprinkle this toner particle, which are nanoparticle by the way. So now they are making this in the nanoscale. All this fine powder that you got onto this charge up device that you got, right? And so it stays on there. So what happened then is that this finely powdered ink or toner heat to this charge, right? Stay on this fuser, and this can then be transferred to the paper. So how do you, in the laser printing, how do you do that? Well, because you have to sort of send electronic signal to your printer to basically discharge, right? So you convert your printing material that your Word document, where it's dark and light. In the light part, you send signal, right? Because on the page that you're printing, the image that you transfer to the fuser, you can create dark and light region. In the light region, you basically have some charge to neutralize, to discharge the extra charge on the fuser, right? And then you can roll your paper and then it just fuse together. So the part that you do not discharge still have toner particle on it, will then get transferred to the paper. The part that you don't want to print anything on, which you discharge the charge on this fuser, you will have no particle on it. So this is how you do printing, and this is how you do xeroxgraphy and laser printing is exactly the same. In xeroxgraphy, you use light refraction. You have a little lamp inside, right? A little lamp inside to refract your page off the page and go on to your toner side. Whereas in laser printing, you just send this image electronically to create light and dark region where you want the toner to stay or not to stay by charging and discharging the fuser that you got. And this is basically done by, so you use, in laser printing, you use a little fine laser to discharge this. So when the semiconductor is exposed to light, the electron hopefully are created and giving rise to photoconductivity. So when the laser, in laser printing, when you move this laser beam around to discharge, effectively you are creating conductivity to discharge the part of the toner that you don't want ink on there, right? So that hence you generate a very nice image that way. So the illuminated layer area will lose the charge and the ink will not stick, giving to right regional copy. So this is how you got photoconductivity, basic photoconductivity work like this. Okay, so that's another application whereby you have surface effect and because you involve a semiconductor material and you have again absorption of light to allow photoconductivity to occur. Okay, so here we have to have photoconductivity. What do you need? You need some sort of a direct band gap absorption. So here you have a material. So in order to absorb a photon directly, you have to have a material with a direct band gap. Okay, and this is why they use this silicium, and special type material, not silicon. You cannot use silicon because silicon does not have a direct band gap. And what do we mean by a direct band gap? You remember we have the electronic structure, right? Various electronic structure. If the conduction band, bottom of the conduction band, align with the top of the valence band, you have a so-called direct band gap. If this align, what do we mean by align? Well, because in K space, at the same K value, if this is at the same K value, that is aligned. But if the band had moved off, different places, then you would have indirect band gap because you don't have alignment on this. And the reason why you need a direct band gap for photon absorption is because of momentum.